So I think last time we did classifications, and in order to, we're done with the perceptron, and we saw some limitations, and because perceptron is not the optimization problems, we want to have classification boundary which is best among the possible candidates. So in that case, we have to think about the optimization problems, and one of them, the first thing is that support vector machine, which is SVM. And in order to talk about SVMs, we have to define the distance in the Euclidean. Distance is in the Euclidean space, distance from the origin and difference from the origin to the straight lines and straight line to any points. Those are, we did kind of the calculations to compute. And the reason why we want to know how to calculate the distance, because we're going to use the distance informations into the optimization process. So that's what we did. And let me show you. And one thing that, again, is I want to emphasize is that for decision-making process, the thing is, how do you find decision classification boundary? If that decision is a straight line, it's a linear classifier, and we can write it. Let me show you. In 2D space, we know that like this represent, it doesn't have to be 2D space. In linear space, it represent in the hyperplane. Okay. And you have to know, you have to understand what's the meaning of, what's the meaning of if P is positive. This is another equations, represent another constraint, represent another geometry, which is, in that case, it's another hyperplane. And we can normalize it like 1. And of course, we're going to have a different, but it's unknown parameter, so it doesn't matter. So we have 3 different hyperplanes. And again, I kept saying that you're supposed to visualize what's happening in the linear space. That's why I know it slightly changed the problems. So we want to find the classification boundaries, but at the same time, we want to find out classification band. That's why, like for A class, another B class, all the data points. That's kind of subtle point you have to think about by yourself. You have to think about it, spend some time. I want you guys to, I want everybody's clearly understand. So like that, that's classification boundaries, like band. And I want to find out this one, an equal amount of distance, like classification boundary, I want to keep like that and set all the data points located, all the other data points are located the other side. Okay, I want find out this one that maximize this distance. That would be the most robust or insensitive. It's going to be insensitive classification boundary. For example, like if I have like this one is, it could be like it's possible, but if you increasing like, okay, so that's the distance. It's smaller than that one. So this one is not the best. This guy is better than the other. Okay, that's the basic idea of SVM. And the first, I want to formulate it in the optimization problems and think about it in this. We can implement it, embed it in that the constraint into the constraint. So like here, it's a subject to. So I put all the data points supposed to satisfy this one. Another data points into another class should satisfy this. And we want to minimize what? Nothing. So I just put anything because right there, those are the conditions that all the data points are supposed to meet. And here I mentioned that those are the same thing. Only difference is that whether we put the constant term is out or bias is outside or we put it inside. So in that case, omega is like omega 0, omega not, omega 1, omega 2. In here is omega 1, omega 2. Those it's basically are the same. The representations are a little slightly different, but it's, as you can see, I kind of assume that all of you guys know what I'm talking. So for that one, so optimization problems, the first thing that you have to think about in your brain is that CBX pi. Okay, so we can implement it, the CBX pi. So these are the conditions. And thing is that we want to minimize something because we don't have any objective functions. I just put one because I have to put something on it. So actually, okay, so it's a trivials, but all things that we put it in the constraint conditions. And this is what we got. This is what we got. This is what we got out of first attempt, which is good because it's we start from the data set is a linearly separable data set. And you can see this is working good. But let's think about another kind of say this. Suppose we have outliers. In real world, some data points has noise or missed errors, outliers, uncertainties, like from any reasons. If do have single data points does not satisfy the linearly separable case, in that case, the first attempt does not give us the right solutions because there's no solution exists. So somehow we want to have SVM or linear classifiers is kind of work for non-linearly separable case as well, to make our method is more robust or insensitive, I would say. So let's think about, we have single data point, which is like in different colors in the other class. So it's too easy that it's too obvious that you guys can right away, you guys know that no solution exists for linear classifier. I mean, you guys can have like that, like, but this is curved, this nonlinear classifiers. I'm not talking about the nonlinear classification yet. I'm only talking about the linear classification right now. So with this straight lines, we cannot find. That's the issue that we have. And as you can see, no solutions. And the idea here is now is a good points that you have to follow very, very carefully to see what kind of like people are thinking to overcome these issues. So we have to allow some training examples to be misclassified. We have to allow some of the data points might be misclassified, but we want to minimize that. We want to minimize those numbers. Okay, that's the key idea. And let's see how the brilliant the people like how they did. Let's see. And we have the same problems, and some of them you know that is have outliers. In that case, for non-linearly separable case, we're gonna relax the above constraint. Don't worry about it if you don't understand what I'm talking right now. I'm gonna show you in a minute. We need slack variables. Probably most of them is gonna be the first time that you heard slack. The slack variables, we have to introduce another decision variables, U and V, where all of them are positive. So those are the key things. I'm gonna show you in the next slide. So the original constraint are too strict. So I want to release some of the constraint, or relax some of the constraint. In order to do that, I'm going to introduce slack variables as well. And let's see. So that's the first attempt that we had. But now suppose we have non-linearly separable data set. And we want to change, slightly modify the problems from here to there. And it looks more complicated. I'm going to show you one by one. So let's say this one. This means that, say, if that's the omegas. So the x1 is that located here or here. Do you guys know? Say number, A, okay. So for that point, is it A or B? Which is located A or is located in B? Because it's positive. And this one is like omega transpose X equal to 0. So probably like there's another one, like band. Because the thing is that we can get a clue from the direction of omegas. So here is positive. So we know that all of the data points are supposed to locate it here. And all the data points supposed to locate it in the B. Right? So which is good. But let's think about suppose this guy is misclassified. This guy is outlier. That means this guy, the true label is like positive, but somehow this data point is located here. Somehow. Okay. So in that case, say this is X, omega transpose X does not hold. Right, because this one is like might be smaller than 1. So if we have U, we assume that U is a positive. Say U is like, if the U is 1, that means it's greater than 1. So A is located like here. If U is 2, this is -1. So A is located that one. So we can make it this inequality satisfied by having right values of U. We can say now we can all the data points we can say we're gonna satisfy these constraints. Okay. In U and V, all of them are positive. Positive. So the maximum value over here is can have 1. If we have right classifications, say A is right here, data points X, then U should be equal to zeros. Why? Because you want to minimize all of the summation of U's and V's. So the idea is that for all the data points, if that's linearly separable, all the U's gonna set equal to zeros, all the V's gonna set equal to zeros, because we do have this kind of objective function. Minimize that. And what if we have small amount of outliers for those data points? Probably it says like these 2 data points is not gonna set if we don't have these select variables. It's not gonna satisfy, so it fails. In that case, U's gonna kick in the constraint to make it satisfy, but those want to minimize those effects. How? We put them in the objective functions. That's the best thing that I can express or explain. And this is a brilliant moment. I mean, when I first studied and learned this one, I said, wow, that's how like people do. So think about, and please, after this class at home, take some time, take the moment to think about by yourself. I want everybody 100% to understand the thinking process, logic process. Okay. So how did I'm gonna put everything expressed in the matrix form, and finally this is what we got. And from that one, why we want to have everything in the matrix form? Because we're gonna use the CBX pi, which is once we have in the matrix form, we can easily implement it in like that. So again, I'm not going to like go through that. What's the meaning of minimize and what's the meaning of this guy? And that's something that you have to do yourself. Well, I'm gonna provide all the necessary materials but eventually you guys have to think or practice to make your own stuff. So that's what out of the CBX pi, the second attempt, this is what we got. As you can see here, even though we have some outliers and misclassified data points, it's okay. In the first attempt, we cannot find any boundaries because it doesn't exist, but now we do have, which is good. But there's, as you can see, I mean, this is what we supposed to get it, because that's the boundary that we start with. So that's not, I mean, at least good thing is the second attempt is able to handle the outliers, which is extremely good, using the brilliant ideas, using the select variables and relax some of the constraint. But the outcome is not exactly what you want. Thing is that the distance for the band is not good enough. It's not good enough. So I wanna, the reason why is that we didn't consider it in objective functions in the optimization process. Somehow I wanna embed it. I wanna consider the width of the band as well. I wanna like as wider as possible. So how do you do that? Any ideas? You guys remember what's the width? You guys remember it? Because I spent quite a time to derive. So if you go back, so further improvement, notice that the hyperplane is not as accurate represented divide due to, so this one is not different from that one. Can we do better? Yes. Now we need to look beyond linear programming. So the idea is that I use width, the term width, but here in SVM, we call it large margins. So margin is like that's those are margins. How do you do that? So the idea is I want to maximize the margin as well. So finally, it's a support vector machines, and distance, margins, and width is gonna be that one. I hope that all you guys remember how we derive that. Okay, I want to maximize it. Maximize the width, the margin as well. Okay, now what we can do, starting from that's what we have up to second attempt, and this one is minimization problems, and we do have maximize margins, which is like that. And the first term we have to minimize, the second part we have to maximize it. I mean, we don't know how to do it, but if you look at this, maximizing this one is the same as minimize this part, right? So I want to change that maximization problems to minimization problems. Now we have two terms that we're supposed to minimize. We want to minimize the first terms and the second terms, and as you can see, there is I think you already saw that in regularization, in the overfitting problems, we have multi terms in the objective functions. Then we can introduce some tuning parameters like weight, things like that. So we do have two terms in the minimization in the minimization objective functions. The constraints are the same as previous one. Okay, and the gamma is that the tuning parameters that which you want to put more weight on margins, or weight on more like outliers, things like that. But having these terms, we can have, not only we can deal with the SVM, can deal with the outliers, but also we can deal with the large margins as well. So again, put everything in the matrix form. So good thing is that CBX pi. The only difference is that now we do have, I think this one is attempt 2, and I include another one. This is a final attempt, and this is SVM. So this is what we can get out of it. It's the first thing is that outliers, and second thing that you have supposed to look for is that how large on the margin on it. It's kind of, we can catch two fish with one stone, or the two birds with one stone. You guys can at home, you guys can, like, by changing these gamma values, whether it's your classification boundaries or band is like getting smooth, I mean narrow or wider or whatever, you guys can see. You guys supposed to do by yourself at home. So in a compact form, I'm gonna skip that one. I'm gonna skip that one. I'm gonna skip because we don't need. So we don't need SVM. I explained the idea is like step by step, starting from the first attempt, and there's some limitations, and which is the outliers. So we introduce select variables. That's gonna be the second attempt. But something is the margins. I want to think about the margin as well. So we add the margin in our objective functions to minimize, maximize it, or it's revert this minimizing it. That's the final attempt, which is final SVM things. SVM is, I would say, for machine learning and classifications, one of the most successful and widely used. And of course, you can see it's already implemented in the scikit-learn. Actually, you don't have to use a CVX-Spy. So like here from sklearns, and we import the SVM, so define kernel as a linears, we can get the same thing. Right? So now let's move on to the further discussions. So far, starting from the perceptron, you guys remember it. Only thing is it's supposed to have linearly separable data set, and all we did is trying to find linear classifiers. Why? Because that's the simplest problems. Because always I want to start with the simplest case to get some good insight out of it. After that, I want to add more complexities. Now it's the time that, what about it's nonlinear separable data set? Then we have to think about nonlinear classifier, nonlinear classification boundary. Okay, so let's think about that problems. And now suppose we have this problem, say this is, so X is one-dimensional space. You can represent that one. And for one-dimensional space, classification boundaries like 0 dimensions, which is point. So suppose, say we have, this is, and then we can see that is going to be linear boundary, right? And if the X is 2-dimensional space, classification boundary is probably 1D. So like what we did like that. So in going back to these problems, as you can see, we need two threshold or points. That means non-linear classifiers for one-dimensional space. So this is non-linear classification problems. Okay. So for linear classifiers, we are not able to find the solutions. Then we are not able to utilize the one that we learned, like for instance, like perceptron and SVM. We cannot get the right solutions. I mean, even though this problem looks extremely simple. No linear separator exists for this data set. Then we cannot do anything. We cannot do anything. Any ideas? Only thing that we is a linear classifier. But data set is not linearly separable. It's non-linearly distributed. So let's think about it. This is another moment that when I studied, and this is another moment that I said, wow, this is brilliant. Right? So each data point or each example is a map from, because this is given data points, I mean given, And we can compute x squared. There's no additional information. So whenever say like x is like 4, then we can have like 4 and 16. I mean, we can do this automatically. There is no additional information needed. Now we have 2 coordinates. Now looks like in 2-dimensional space. Suppose like this is the origin, then we can now in 2D space x and x squared. Now we, because remember like in like this shape, right? So if you use colors, probably these data points it's like that, and this green is like that. Now just forget about the original problems and think about this. Now data points, given data points are located in 2-dimensional space, and you can find linear classifier. Now, this one we can do. We can use perceptron or SVM, whatever, any kind of linear classifier we can do. And once we do, now let's go back to the original space. So in that case, let's go back. And this is the nonlinear boundaries, classification boundaries, and like that. Okay, we don't have any nonlinear classifier. We don't need to learn how to do it. Instead of doing that approach, what we're gonna do is that we're gonna, in nonlinear distributed data set, we're going to have another mapping to another space, hoping that in that space, those data points are linearly separable. As long as that the data points are linearly separable, we are able to find hyperplanes, linear hyperplanes, using SVM, for example. Once we have that, going back to the original space, then the boundary is going to look like nonlinear classifier. Okay, that's the idea. Looking at another example, now we have the original data set in 2-dimensional space, original data set, and looks like this is going to be the good classifiers, but it's not linear. But if you have this kind of mappings, now now from 2D to 3D, 3-dimensional space, probably is data point redistributed, rearranged like that. Now we can find linear hyperplanes. One missing part is that I'm not going to show you how do you find good mappings. I'm not going to show you. So if we suppose we have a good mapping functions, the data is become linearly separable in new representation, in new dimensions, in higher dimensions. In general, it has to be higher dimensions. So the mapping functions, we call it kernels. I mean, I guess this is the first time you heard of kernels, but don't worry about it. You don't have to know. So that's the specific name in machine learning communities. So it's kind of, you can think of mapping functions from non-linearly distributed data set. If you have right mapping functions or right kernels, you can have linearly separable data points in higher dimensions. Here, just remember that one. Make linear models work in nonlinear setting. And I'm gonna show you short movie clips. I guess this is absolutely, like, if you watch this, understand this one, you guys 100% you guys clearly is able to understand how nonlinear classifier works, right? Now, as you can see, in two-dimensional space, data points are nonlinearly distributed. Red is outside and blue is inside. Now, apply corners that re-represent in three-dimensional space like that. Now, it's in three-dimensional space, linearly separable. We are able to find linear class hyperplanes or classifiers. Now it's going back to the original space. Now that boundary looks like nonlinear. So that's done with the nonlinear classifier. So there's no such nonlinear classifiers. There's no. Only the method you have is linear classifier. And before that, you have to come up with the good corners, right? That's the additional things that you're supposed to have when it comes to nonlinear classification problem. Okay, and suppose we have this kind of data distributed, and as you can see, probably if I ask you draw the nonlinear classification boundaries, probably we want to draw like that, right? But as you can see, this one is not linear classifier. And so here, let's say I'm going to use SVM for linear classifiers. But before that, we need to have corners to remap. So in that case, from two-dimensional space, like 3D space, this is like additional things. So here, if we utilize this given corners, and this is what we got. This is what we got. Go back to, so let me see. These are the original data set, and Z is remapped the data points, and you can see I apply the SVMs in data points in G space. Okay, that's what we got. And the question that you guys might have, how do you find the corners? So for nonlinear classification problems, the key thing is that how do you find good or appropriate corners? That's the really critical step. But for this class, don't worry about it. If I give you the nonlinear classification problems or exams, whatever, I'm gonna give you the corners as well, along with. So don't worry about how to find the corners, all right? Okay, that's all materials that I have for SVM. Any comments, any questions you guys have? If I move on to next topic, which is logistic regression.